So we've had some time to explore conservation of energy. We worked out the equations, we practiced them with a couple of problems, and we've also played with the FET skateboard park, and I'd recommend you play with that a little bit more on your own. In fact, when we played with it, we found that the conservation of energy principle just tells us that I can take a system, this is my system, this field with my skateboard park, make that my box with my energy contained in that system. And if I start the skateboarder up top here and let him go, I've actually graphed in time how his energy changes from one form to another as he goes up from high to low. His potential energy goes from high to low, and his kinetic energy goes from low to high, and then it reverses itself and he goes up this path up the hill, and he drops down to a low kinetic energy, low speed, but a high potential energy, a high height. And then he reverses that again. And you can see that over time in these graphs that we made. And this is one snapshot in time. In fact, it's a snapshot in time of him standing on the hill right here. You can see the breakdown of the components between his kinetic. He's just starting to gain some kinetic, but he still has mostly potential because he's still up fairly high in the curve. And these two bars would add up to this bar right here. I think I got clipped off at the top of that with that bar. And we get thermal energy, we found, when, number one, we add friction onto the track. We would get thermal energy if we had air resistance as well. Thermal energy is just the motion of atoms, and moving the air around has the same effect. And we'd also get thermal energy if we have a collision with the track. If somehow we jump off the track and land on it again, we saw, like when you hit those two big metal balls against your papers and burned holes in it, we have a huge drop in our energy that's in our mechanical energy, and it gets transferred into thermal energy. And think of also as well energy like sound that is emitted from the situation and vibrations in the track and things like that. We could have those forms of non-conservative work being done. So that was a lot of fun playing with that. In fact, there's some bonus associated with that. If you can actually come up with a loop-the-loop that's approximately the same height as you see up here, your loop-the-loop has to be 90% of your original starting height or higher. And so make a big loop-the-loop here and see if you can get the skateboarder to go through the loop-the-loop. And if you can do that, you should take a video tape of it and explain what design process you worked on to, as I'm sure you'll start someplace and you'll end up at another place, and you should briefly explain what happened. If you can explain the physics behind it, that'll be worth some better bonus points. If you can get a double loop instead of a single loop, that's 90% of your height. That will be worth even more. So the previous examples that I showed you, we were able to use either conservation of energy to solve a problem, or we were able to use our good old friends, the motion equations, to solve problems. I'm going to show you some cases where you cannot use motion equations, and conservation of energy equations are really easy to use. But if you did try to use a motion equation, you'd find them to be quite difficult, if not impossible, and you'd certainly need some calculus for the problems we're coming up to if you were to try to use any type of motion equations, and you'd have to drive some new ones yourself. So our first example, I set up in class a pendulum bob. So I just took a 200-gram mass attached to a 1-meter string, and we can let the bob swing on the string. We hold it horizontal, then we let it go. So our initial velocity on this is 0, and we're going straight down to start with. And the question we'd like to answer is, what are the speeds of the pendulum bob as it gets to point B, C, D, E, and later on, how high would it go to point F? And you'll notice I've taken some easy points here. These are 30-degree angles. It'd be easy for me as well to put in a 45-degree angle, so you wouldn't have to use a calculator that much to solve any of these problems. But there's nothing to say we couldn't use some oddball angle like 23 degrees or something like that. Just use SOHCAHTOA. Some questions to start out your thought process is, are there any assumptions you need to make? Something that you might want to think about is, where is the maximum speed of the pendulum and where is the minimum speed of the pendulum? I think these are pretty easy questions to answer. And then ask yourself, what method would you use, given what you know now, to solve this problem? For example, could you use free fall for this problem? And the answer is no, because this is not free falling. Remember, free fall means you only have one force acting on it. It's a force due to gravity. Others are negligible. For example, air resistance. And air resistance in this problem is negligible. Our pendulum bob isn't moving that quickly. However, there is another major force acting on this, and that is the tension of the string. You have a string that's pulling back on this thing. So we know that it's not a free fall situation. Well, that being said, is it a constant acceleration situation? Maybe this is still another form of constant acceleration. I can still find another way to use our constant acceleration equations. Well, we'll look at that. So a couple of questions we could ask, little side questions here. So let's compare our situation with the pendulum bob to a ball that we're going to drop straight down for 1 meter. First, I'd like to know which ball would be going faster at the bottom, the one on the pendulum, which is swung down through this quarter of a circle, or the one that drops freely in a free fall down 1 meter. Number one, the free falling mass goes faster when it reaches this point. Number two, there are equal speeds. Or number three, the pendulum bob is moving faster when it's down at this point. Another good question you could think about is, what about the tension in the string when we're at point D? What's the tension in the string going to be? And you might want to start, before you answer this question, draw a free body diagram at point D and work out the forces at point D. I'll tell you right now, the force due to gravity on this is going to be 200 grams, 0.2 kilograms, times 10 meters per second squared, or 2 newtons. So here are your options. Is the tension of the string going to be 2 newtons for the tension of the string, just equal and opposite force due to gravity? Will the tension be somewhat less than that, or will the tension be something more than that? A third question you could ask, but I think everybody can answer this one fairly easily, is which one would reach this point down at this level position down here first? Would the free-falling object reach this point first, or would the pendulum swinging down through this point reach first? And all three of these we could demonstrate in class and experimentally determine which is the fastest, and so on and so forth, using our CPO timer and some other equipment, and we will do that in class. Well, first of all, when it's starting out, it's moving downward initially, and it will be accelerating initially just as if it's in free fall, and the velocity initially is 0. Another thing that you've probably found is that as we swing along this path, its motion follows this path, its velocity is tangent to this path, and we call that a tangential velocity, and it's accelerating along that path as well. We call that a tangential acceleration. We can draw those vectors in. And this acceleration is caused by one thing. It's caused by the gravity acting on the ball. Now, here's the thing. The gravity is the same the whole time. It's always acting with 2 newtons downward. But as we swing through this path, the component of the gravity that's actually pulling it along the path changes. And so we need to break these down using vectors to a portion that's tangential to the curve and perpendicular to that tangent. We call that perpendicular to the tangent. We call that a radial direction. So here's the force due to gravity acting on the objects from points A, B, C, D, and E. And what I'll do is I'll break this down into a portion that's parallel to the path and a portion that's perpendicular to the path. And remember, if you were to translate these over to the center of the ball, you could see, if you moved all the red ones to the center of the ball and all the blue ones starting to the center of the ball, the blue ones would all be radially pointing outward from the circle, and all the red ones would be pointing along the path as if they were drawing small tangents along this path. You'll notice my color coding here. Anything that's red is tangent, and anything that's blue is perpendicular, or what you call a radial direction. And two interesting points are the ones we're looking at first. Are at points A, our force due to gravity is perpendicular to our path, it's tangent to the curve. And at point D, it's actually radially directed away from the curve. So it's just the opposite. So we have a 90-degree angle here and a 180-degree angle here. Very important. So if the acceleration is caused by the force of gravity, we know that it would be proportional to that force as well. Newton's second law. So here our tangential portion of gravity is quite long, and as we get to point B, it's shorter. Point C, it's shorter. Point D, we have actually no tangential component, which would indicate that our acceleration at point D is 0. Another way to think about this as being 0 is that we are speeding up as we come down to this point D. But as soon as we pass point D, we start slowing down. So we must have gone from a positive acceleration on the right side of this to a negative acceleration on the left side. And so in the point in between, we must be at 0. So acceleration is not constant. We start at negative 10 meters per second squared for a tangential acceleration up here. We end up down at 0 down here. So we are continuously changing our acceleration. There's nothing constant about it, so we cannot use constant acceleration motion equations from Chapter 3. Now, if an extra credit activity, you folks have better math skills and maybe some calculus under your belt, can you come up with an equation which would give you your acceleration as a function of your angle, or as a function of your height possibly, and use that to derive acceleration, velocity, and position equations based on that are not for constant acceleration equations. Another thing that you will find out, and you can try this at home if you happen to have a swing set in your backyard. Jump on a swing, have a friend push you, and try to get a little bit of speed on the swing, and you'll find that when you are at the bottom of the swing, you feel really, really heavy at the bottom of the swing. And if you really feel heavier than normal, that means that the tension in the ropes that are holding the string are also heavier than normal, and the tension is going to be higher than normal. You'll have a tension of the string that will be pointed radially in, and you'll have gravity, or a portion of gravity in these other cases, pointed radially out. And at the bottom especially, you'll see quite a large difference between the two. And that's really strange, and that's something we'll discuss more in Chapter 7. And if you go to Canopy Lake Park, can you think of some other situations where exactly the same situation occurs? Finally, what if we just clip the rope and let this thing drop from point A down to the floor in free fall in 1 meter? And so we can just toss it into our free fall equations, and we find that the velocity at the ground is 4.47 meters per second after a 0.447 seconds. Easy calculations for the free falling. So let's see how we would use conservation of energy to find the velocities of the pendulum bob at point D. And we're going to use the equations, the conservation of energy equations. Later on you'll see I'll show you how to use a table to do this. Actually, the first thing I write down is conservation of energy, then right below it I'd write this formula. And we're going to start by finding the velocity at point D. We could also do this for point B, C, E, or F. Total energy at A is equal to total energy of D. That's what you want to write down first. And we can actually fill in what the total energy at A is and what the total energy at D is from our various forms of energy that we have. And what we have for A is we have some form of kinetic energy, some potential energy, and potentially some work non-conservative going from A to D. And on the right side of the equation, we have our later point. We have some kinetic energy at D and some potential energy at D. We could substitute in for each of these an equation. We know an equation for kinetic energy. We know an equation for potential energy. For work non-conservative, it depends on the form of work non-conservative. If it's friction, for example, we could draw a free body diagram and figure out the friction using our normal free body diagram methods. If it's a pushing force, potentially we could do the same thing. If it's a rocket, it might be a little bit more difficult. If it's a fly buzzing on it and making it move, that might be something more difficult. And so you'd have to play this by ear for the work non-conservative. Remember, work non-conservative is from forces that are not conservative, they are not recoverable energies. On the right side of the equation, once again, we have some kinetic energy and some potential energy, and there's our formulas for those. Now, typically what I'll do is I'll ask which values are zero. And when you get better at this, you'll zero things out in this first line rather than the second line. And you can save yourself some time writing all this excess work down below. So let's just see which ones of these are zero, which ones aren't. Well, first of all, we know our velocity at point A is zero, so our kinetic energy at A is zero. Secondly, let's see, we've got a height at point A. Well, our height at point A is not zero, so that stays in. Well, let's look at work non-conservative. Well, work non-conservative, do we have any friction going on here? Do we have any air resistance? Are we scraping against the board as it falls? Is it making any sound? Is it vibrating anything? Well, let's assume that all those are negligible, so I'll zero that out. Now, if it's not negligible, well, what would happen for point F? If we have no non-conservative work done, we should end up at the top of our curve here again. However, in reality, when we see the swinging in the classroom, I always end up hitting the board, or you have a little bit of flexing in the rope that's going to cause some frictional forces, some internal friction, and heat up that point right there. You've got a little bit of air resistance. All those will bleed off a little bit of the energy that you have, and you'll end up going a little bit lower. So in reality, this is not going to be zero in a realistic situation. How about our velocity at the bottom? Is that zero? Obviously not. That's our maximum velocity for the situation. How about our height? Well, our height, we've got to decide what we want to call zero for our height. And so I'm going to pick point D. I'm going to draw some axes just like we always do. It's still important to draw axes in these problems because we need to know heights when we're working with energy, especially potential energy due to gravity. So draw potential energy. For potential energy, draw your XY axes, pick out a zero. You can pick out a zero at point D. I don't care if you picked out a zero at level A or level B or level C or way below or way above. Wouldn't matter as long as you're consistent with your measurements of the heights from that 0 point later on. It would all work out. So given that's our zero reference point, at D we have a zero height, so our potential energy at D is zero. And like I said, I would recommend, once you get used to this method, you should zero out things up here. Just walk through your head. Is my velocity zero? Yes or no? Is my height zero? Yes or no? Do I have any non-conservative forces going on here? Yes or no? Velocity zero? Yes or no? Height zero? Yes or no? And knock them out here. Then you'd only have to write in the parts that are remaining down below. And so there's what we're left with. We only have our potential energy at the top should transfer into our 100% of it should transfer into kinetic energy down the bottom. At this point, this is a great time to plug in numbers. So on a quiz or a test, I need to see this amount of work to start with using equations, and then feel free at this point to plug in numbers. And I really do like to plug in numbers at this point because when you do, you can actually calculate the amount of energy at each one of your stages and compare them and see and get a good realistic idea of how many joules are in different situations. So let's do that. So when we plug in numbers into our equations up above, and remember we're using our numbers of our mass is 0.2 kilograms, gravity is 10 meters per second squared, our height was 1 meter. And we can see when we plug in some numbers and calculate, we've got 2 joules of energy that we started with at 1 meter high for this 2.2 kilogram object. And we don't know what our velocity at point D is. That's our unknown that we're solving for. And once we get that, we can easily see how to do that. You'll notice here, so we started on the left side. Here's our starting point. Here's our ending point. We started with 2 joules of potential energy. And all of that 2 joules will get shifted into kinetic energy right here. And so we can solve this for VD, divide by 0.1, take the square root, and you get 4.47 meters per second. Do you recognize that number from someplace? The other thing we could do is we could find a general solution for VD. All right, so let's do that and let's compare. So we're going to start with this equation. And the first thing I'll do, I'll look at this equation. If I'm going to solve for VD, what would I do first? Well, there's something that cancels here. It turns out mass cancels. And you can ask yourself, when would mass not cancel for a situation like this? Well, a couple instances you should consider. I'm assuming in this case that the mass that we started up at A is still all there at point D. If we were to lose some mass along the way, and there's some certain situations where that would happen in real life, then you couldn't say the mass here and the mass here are equal, and you've got to use some different techniques. However, in many cases they are the same. Another time we wouldn't be able to cancel mass is if I had another term in my equation here that didn't have a mass term in it, and you will see later on when that'll happen. I'll let you watch for that and figure that out. In this case, though, mass is constant throughout, and I have a mass in every term, so I can cancel, divide mass out of both sides. We're left with this result. Let's solve for VD. Just multiply by 2, take the square root. And there's our solution. You'll notice I did put a plus and minus sign in here, because we have a squared number here, and we can have a positive velocity or a negative velocity, and when we square it, that sign will disappear, we still get a result. Also keep in mind, when I'm writing out G here, that G is the magnitude of gravitational acceleration. There is no sign on that G that is a magnitude only. We can plug in for our height 1 meter and work these things out, and we get our result VD equals 2 times 10 times 1 to the square root, and I get plus or minus 4.47 meters per second. Do you recognize that number from any place? Well, it's the same number we had as the 1 meter free-falling ball drop. So, crazily enough, it turns out that it doesn't matter if you let this ball swing from A to D on this curved path or let it fall straight down, you end up getting the same speed at the bottom. The question to you is why? And you might want to think about what was doing the work along the way here. Look at the forces, look at the free body diagram, see what was doing the work, and you might be able to figure out an answer for that. We talked about that in class already. It's good bonus questions, it's good quiz questions. So now let's take a look at point C and see if we can use the same type of method to find an answer at point C. We want to find the velocity at point C. This you're supposed to do for homework. Same starting point, we're going to find point C. So you write down the words conservation of energy, then write down this equation. Total energy at A has to equal to total energy at C. Don't write down this longer one. That's just to show you that any 2 points are the same, but we're only going to look at, when we use this equation method, take 2 points and compare them. So we're taking A and C and comparing. Here's our components of energy at A and at C. For A, we have kinetic energy, potential energy, and if there's any work non-conserved that happens as we go from A to C, we put this on the left side of the equation. On the right side, we have kinetic energy at C, and we have some potential energy at C potentially. Now, here's our equations for each, and we did this on the last problem. And once again, my next step is to zero things out. And remember, as you get better at this, you'll want to zero out of this equation here where we have KE, PEs. It'll save yourself some writing down later. And you ask yourself for KE, which ones have zero velocity, for PE, which ones have zero height, and is there any work non-conservative done? So which ones are zeros? And so we have no velocity at point A, so the zero velocity starting point, so our kinetic energy is zero. Assuming we're going to start our height at D to be zero, our height at A will be non-zero, so we'll have some potential energy due to gravity. We're going to assume once again that our work non-conservative is done. No friction, no loss in the rope, no sound, any other types of bumping or vibrating going on. Even though we know that in reality it's not true, we do lose a little bit to work non-conservative. Our kinetic energy at the bottom is non-zero. That's what we're trying to find. And our potential energy at the bottom, we're not going to be down at zero. If we assume our zero is down here, we have 1 meter of height here. We have some height here that we'll need to figure out. So that's non-zero. So we can't zero those out. So we're left with 3 terms in our equation. And once again, this is a good time to plug in numbers. I love to plug in numbers in these type of problems because it shows you how much energy you have in each point. And you can see how the energy is being transferred from one form to the other. So plug in some numbers, and what you find out is our initial potential energy due to gravity, which is sitting right here, is 2 joules, just like we had before. And we have our velocity, which is what we're trying to find. Here's our kinetic energy term. Don't know what that is. And I magically came up with a number of 0.268 joules for our energy at point C, or potential energy at point C. Now, I know that my height at point C is 0.134 meters, and when I go through the general solution, I'll show you how I got that number. So trust me for now, and you can see what happened here is our potential energy started at 2 joules, and over here on the right side at point C, our potential energy has dropped down to 0.268 joules. So most of our energy has been transitioned into kinetic energy. And we can easily solve for VC, and we find out that the velocity is 4.16 meters per second. Well, that's a good number. We know that at the bottom it was 4.47 meters per second, and just before the bottom, we know that's our bottom should be our maximum speed, and so this should be somewhat less, but we're pretty close at the bottom, so we know it should be a somewhat small number, but fairly close, and it is. And so that gives us a good idea that both our numbers are in line with each other. So we could also find a general solution, and when we do the general solution, I'll show you how I came up with the heights. So first of all, in our general solution, once again, mass does cancel out in all of our terms. We can factor out a mass or divide everything by mass on both sides. It would all cancel. And as I mentioned before, there are situations where we don't have a consistent mass throughout the problem. And there are times when we'll have an extra term, especially if there's work going on with this situation. Or maybe there's another form of energy that doesn't have a mass term in it. Hint, hint. Cancel this out, we'll come up with a general solution, so mass doesn't matter in this particular situation. If I collect all my gravitational components over to the left side, you see I already shifted this over. I multiplied by 2. I factored out a common g for both of these, and I have 2g times my height at A minus the height of C equals VC squared. Now this looks very close to what we call delta H. But delta H, when we solve for VC here, delta H is actually my final minus my initials, HC minus HA. And so this is HA minus HC, so this is actually negative delta H. That's why you see I took and replaced this factor here with delta H with a negative. And you can see I get this nice general solution here that says my velocity at point C is just plus or minus the square root of negative 2g delta H. And the question is, what do we use for H at point C? Well, at point A, we're going to use 1 meter, so we'll use 1 meter for our and delta H for A. And remember, we do the final minus the initial, so I need the final height. I need this tiny little height from here to here, and subtract it from this 1 meter here. And which is a good thing. This tells us our delta H is going to be negative because I've got this small final height and I've got a large initial height, and so that's going to be a negative number here to cancel that negative out, and we'll be able to take the square root of a positive number. Remember that g is the magnitude of our gravitational acceleration. There's no sign on this. So, big question that probably some of you are asking is, how do you find the height at B, C, and E? Well, this is just like a unit circle, so use your skills of a unit circle. You've got special right triangles hidden in here, so if we draw, these are the heights we're trying to find. We need to find the height at point C. And by the way, we can use a little bit of symmetry. The height at point E is the same as the height at point C. How do we find the height at point B? It looks somewhere in the middle here. Height at point A is 1 meter. That's easy enough. Well, let's use some special right triangles here. We've got a couple of right triangles. And these are both 30, 60, 90 triangles. And our 30, 60, 90 triangle, the hypotenuse on both of these is the length of your rope, which is 1 meter. And knowing that's my hypotenuse, my short leg is always half the hypotenuse, so that's going to be half a meter in this case, and this length here will be half a meter. But this length here is going to be square root of 3 times the short side, so it's going to be 0.8660 meters. Now, this isn't actually our height. This is actually our height from here to here. So we've got to subtract 1 meter from here to here. From that, we're going to subtract a 0.8660, and we're going to get our 0.134 meters. And that was the 0.134 meters I showed you before. And there's our 4.16 meters per second we saw earlier. So conclusions. We found that we came up with a nice general solution here. The question is, how useful is this? Can we use this in many other situations, or is it stuck to a problem just like this? Well, let's think about this. What restrictions did we have on this problem? Well, we didn't have to worry about free fall, so it doesn't have to be in free fall. It just had to go between 2 different points. It doesn't matter the order of the points. I can go from low to high or high to low because my delta H would take care of that. I did have to assume that there was no work non-conservative being done, and the only forms of energy were potential energy due to gravity and kinetic energy. But other than that, we should be able to come up with a result for any of these types of solutions using this general solution. So here's another question. Does the plus or minus have any meaning here? So I threw this in. Mathematically, since we were taking the square root of a squared number, there'd be 2 answers. But do we actually get 2 answers out of this? My argument is yes. Here's positive VC as we're swinging down, and when we come back through the other way, as it swings back around from A, B, C, D, E, F, then F, E, D, then back to C, we're going to be going the opposite direction. If we haven't lost any energy due to friction, air resistance, so on and so forth, we should have the same velocity in the opposite direction. So we actually do have a little bit of directional information here, but generally speaking, energy calculations, remember, energy and work are magnitudes only. They are scalar quantities. They don't have any directions associated with them. In this case, we can actually interpret what the directions mean with the velocity because we have a diagram we can associate it with. So we can infer the directions for velocity and acceleration based on a diagram that we drew. Now, does the energy method find time is the other question you could ask yourself. And you'll notice that energy equations don't have any time components in them. So one of the restrictions of energy equations is we have no idea what the timing of these things are. So even though we know what the speed is at point D, we have no idea of how long it took to get there. And we have to use some other methods to find that. And we'll find that we have methods to do that later on. Now, let's look at another way of tackling these problems. And this is called the table method. And as I had mentioned in class probably, I came up with this method my first year teaching about 15 years ago, 2000, 2001 time frame. And this method, basically I was working things out in an Excel spreadsheet, just trying to generalize some things for the students and show them and plot some things. And this is well before the FET Energy Skateboard Park came up with its nice, I don't think Java even existed back then. So I was actually mapping out these things in a computer form, so I could actually plot these things out, sort of like you saw this graphs in the FET Energy Skateboard Park. And what I found was this: there's a nice little process that you could use to go through and find out the energies at any points. And I'm going to step you through that process. You have this blank table, and we'll step through this and see how this table works. So the first thing you want to do on this table is you'll notice in our rows and columns that I have a height of the object and the potential energy to gravity of the object, the velocity of the object, its kinetic energy of the object, and then the total energy. On the labels for the row columns, the rows are just the points that we're interested in, points A, B, C, D, E, and F for this situation. So the first thing you can do is write in equations. And I'm going to start with the energy equations. PE equals mgh, K equals 1/2 mv squared. And our total energy is the sum of these other two energies, potential energy and kinetic energy. And I can solve for V based on kinetic energy and come up with the square root of 2 KE/m. And using PE equals mgh, I can solve for H by just taking PEG and dividing by mg. And of course my units are as shown. So the next thing I'm going to do is, you notice I'm changing colors here. Anything new that I'm doing here will show up in red. Any of the old answers that I already put in will show up as green. So the next step you'll do is take a look at all the heights and the velocities in your diagram. And sorry, it's not easy for me to flip back over to my diagram. But at point A, we were at 1 meter high, and we started at 0 velocity. So we knew both of those, so I plugged those in here. At point B, for example, when we work out those geometry with those triangles, we know that's at 1/2 meter high. We have no idea what the velocity at that point is. That's one of the things we need to find. At point C, we used another special right triangle, and we found that was 0.134 meters high. Once again, that's one of the unknowns of velocity. Don't know that. Point D, we were at 0 height. We defined D as our 0 height, and our velocity at that point is unknown. That's one of the unknowns we wanted to find. At point E, we're back up to the same height we were before at point C, and once again, we have an unknown velocity. At point F, our question was, well, how high will point F be? But we know at its maximum height, it will slow down to 0 before it turns around and goes backward again. So there's where we start. And our next step will be to take these numbers, and we'll plug them into our energy equations for the numbers that we know and calculate the energies associated with those. So, and please show some work, and you can see I showed my work in a couple of cases here, just to show that I know what I'm doing, and I can see where you're making your mistakes, if any. So every point where I had a number in my height and velocity column, I went ahead and calculated the energy associated with those. And I should have a 0 joule energy plugged in down here as well. So easy enough, plug into your equations up above. All right. The next step is we're going to look at our total energy, and we actually have, if you noticed, there's one column, there's one row, and there's hopefully, and any problem you do, there'll be one row that has every energy filled out, and that will tell you what your total energy is for the situation. And so I'm going to use that total energy for the situation. And once I figure out the total energy by just adding my potential and kinetic together, which I knew both of these, I can actually take that total energy, because it never changes in a situation where there's no work non-conservative being done at least, and I can just drag that down and copy them into every single cell below. Okay, next step is I can work backward now. If I stay on this step for a second, now I have the total energy here. I know the potential energy, so I can back into see what my kinetic energy is and use a little subtraction. Same thing right here, same thing here, same thing here, and same thing over here. Remember, I should have it 0 joules in this spot. I left that out by mistake. So what we have here is I did that. I took 2 joules. We know we have 2 joules here, so I have 1 joule here. So I've got to have 1 joule here to make up the difference. I have 2 joules here. I have 0.268 here that I calculated early on. I obviously have 1.732 joules here. And you can step through for the rest of these and see similar results, just a little subtraction. Now I have all of my energies filled in and all of my known values filled in. And so let's look at our unknowns. Well, for example, our first unknown is, what is this velocity at point B? Well, our velocity at point B, don't know what it is. I have a little equation over here up top. It's a square root of 2 times my kinetic energy over my mass. And my last step that I just finished was finding that kinetic energy. So I can toss this in my equation, calculate. Same thing for the rest of these situations. I can use my energies that I know and back into my velocity or back into my heights. And that's what I did in this next step. And here are the results for the situations. And these are the same answers that we found before. At point D, we had 4.47 meters per second. At point C and at point E, we have 4.16 meters per second. They're both the same level. You notice I left out a plus and minus sign here. But we do know that in this particular situation, we have a pendulum, so it's going back and forth. And so some points it'll be positive, some points it'll be negative, as however you define positive or negative to be. Over here, we were able to figure out our final height based on 2 joules of energy. And you'll notice that this line here at point A and line F are the exact same values. So if we're not losing any energy due to non-conservative forces, then we will end up having our starting height and our ending height to be the exact same. That's the table method. So when would you use the conservation of energy versus the conservation of energy table? Well, we'd use equations if we only have 2 or 3 locations to compare. They're very quick calculations, especially if there's only 2 locations to compare, even if there's 3. So let's say we had a little loop-the-loop or something like that. If we wanted to compare points A to B or A to C or C to B, we could do that just by writing down our total energy to A equals total energy to B, or A to C or C to B, whichever pair you'd like to compare. Toss in some numbers and work out the values. And the pros of this situation is that we can find a general solution really easily, and we can also find quick values for the energies at any point on the curve quite easily. So this is, in fact, if you're working on AP tests, I would not use an energy table. I would use this method, because typically they're not asking you for 15 different values. They're only asking for 2 or 3, and you can quickly and easily, especially when you have 2 points you're comparing, work out these equations very quickly to get a quick answer. A table, on the other hand, is very useful if you have 3 or more locations to compare. So if you have lots of locations you'd like to compare, see what's happening, it's a very valuable method to use. So for example, if we have a loop-the-loop and we've got several points on the loop we'd like to analyze, A, B, C, D, E, F, G, H, I, maybe we're going through a free fall path as well, we could fill in a table and work out our answers. And the advantage of this situation, it allows us to see how energy transforms from one form of energy to another right in a table form. We can actually see the values firsthand and actually watch that energy move from one point to the other. You'll see later on, you'll have a homework problem related to a situation just like this, and I call that my Evel Knievel problem. Let's just look back at the energy table to show you what I mean by seeing the energy transitions. So as you can see, at point A, this was when we were at the top of the pendulum bob. We had all potential energy, 2 joules. We had no kinetic energy, 0, and our total was 2. We swung down halfway, so half of our energy was lost in potential, and that other half shifted over to kinetic. As we swung down even further, most of our energy was now gone from potential, and most of it was now shifted over to kinetic. As we reached the bottom, we had absolutely no potential energy left, and we had 2 joules that was all in kinetic energy. As we started swinging back up the curve a little bit of the way, a little bit of our energy shifted over to potential again, and we can see our kinetic starting to drop. When we swing up all the way over the other side, our kinetic energy drops all the way to 0, and our potential energy jumps right up to its initial high value again. And you can think of that as our skateboard park, or maybe as a half pipe or something like that. Speaking of a half pipe, I gave you a homework assignment to analyze this frictionless half pipe, and I asked you to use conservation of energy equations and use a table. You can actually figure this problem out. And I think this is a pretty straightforward problem, so I'll leave that to you to do. And we already looked at this in class as well. Let's take a look at the more interesting case where we add some friction. We've got a skater that's 70 kilograms. He starts at point A, and there's no friction on the curved surfaces, but we do have friction on this flat surface at the bottom where it's red, and we have a mu k that was given to us of 20%. So the question is, what's this skater's speed when he reaches point B, point C, and at point D? How high will he go at point D? And this is a different situation than he had before. When there was no friction, he's just going to swing back and forth through this just like a pendulum because he loses no energy. When I say lose, I mean it's still in the system, but it's perhaps transitions into a thermal energy that we have a hard time recovering. It's not recoverable, so it's non-conservative. So in this case, when we go from A to B and B to C, we'll actually be losing part of our energy due to thermal energy along here, and as a result, we'll have less speed at point C than we had at point B, unlike the frictionless half pipe in which you would have the same velocity along the bottom. And if you have less velocity, that means we have less energy at this point, and we will end up going up to a lower height at point D. Same thing when we reverse our direction and come back down, we'll have the same height here, same speed at point C as we did when we left to go up to D. Then we'll have to transition across our sticky surface again and lose some more energy, so we'll be even slower at point B, and then we'll go from point B up to even a lower point than we did when we were at this lower point over in D. Then we'll turn around, come back, go to our sticky surface again, and back and forth, back and forth. Every time we cross and pass a sticky surface, our friction surface with mu k equal 20%, we're going to generate some heat, which we lose from our kinetic and potential energy pools, and our thermal energy bar will grow and grow and grow, and eventually will come to a stop. The question is, where will they stop? How many times will you make it back and forth? Where will you stop, and which direction will you be moving when you stop? And if you think about this, there are some patterns that you can use to solve this problem very quickly once you get a few steps in. And let's take a look at that. So let's practice using conservation of equations of energies first, just to show the comparison between the two models. So for conservation of energy, we'll start by finding the speed at point B. So we'll take the total energy at A, set it equal to total energy at B, toss in our equations, zero out our initial velocity is 0. From A to B, there is no friction, so we'll assume that we don't lose anything to work non-conservative. And at point B, we have 0 height, so our potential energy to gravity is 0 as long as we define our 0 to be there. You'll see later on I'll put in an energy reference. And that slims down our equation to this manageable amount. Our masses end up canceling. We can shuffle things around a little bit. Solve for VB. You'll notice I have a VC here by mistake, and that happened because I cut and paste this because it's the same general equation we had before. If we have a height transition from one point to the other where we only have kinetic energy and potential energy involved, then we have this general equation that works. And I'm just showing that again. So this equation works. And here's our height reference that I referred to before. I'm using 0 height as this baseline here. We could put 0 height anywhere, we could still use this equation. At point C, we've got a different situation. Now we've got a work non-conservative term that's going to be in here. We can't, we've got to take care of that. So we've got work non-conservative going from point B to point C. And the question is, how do we find that work non-conservative from going from B to C? Well, to find that work non-conservative, just write, anytime you work non-conservative, because it deals with the force that's non-conservative, draw a free body diagram to see what those forces are. We have force due to gravity. That's where I like to start, as you know. We have a normal force. It's counteracting it. It's going to be equal and opposite. It's a nice level surface. Sorry about the extra equal sign in there. And as we slide across here, the only force acting in the horizontal direction will be friction. Nothing's pushing us here. We don't have a rocket motor attached, or there's no dog pulling us, nothing like that. Of course, those would be other sources of non-conservative work as well. And so our non-conservative work, we have our displacement is going to the right. these two vectors, these two blue vectors, are perpendicular to our displacement vector, so those will be doing no work, and it's really only this vector here that is doing work for us. So we only care about our work done by the frictional force. And so the work is done by friction, so we can just say work non-conservative equals, well, what's our work formula? F times d times cosine of theta. And so force due to friction is, remember, cosine of theta would be a 180-degree angle here. That's where our negative sign comes from. Our mu comes from the mu times Fn, and Fn is just m times g, so we get negative mu k mg times d. We can plug that into our equation. So you'll notice here that I chose my starting point here to be point A, and my ending point to be point C, and we've only got work non-conservative going from B to C. There's nothing that says I couldn't actually go from total energy at point A to the total energy at point C. Once you know your answer for the velocity at B, you could do that. Because I didn't actually come up with a number here, I'm going to just use my guys at point A. Is why I just started at point A here. And as we know at point A, our velocity is 0, and at point C, our height is 0, so those two are going to drop out. And so we have this formula. And once again, this would be a good point to start plugging some numbers into figuring these numbers out. But you'll notice mass still cancels out in this case. Our frictional force has a component of our normal force in it, and the normal force is related to gravity, which is mass times gravity. Even if this were at some sort of angle, we'd still have a mass component in here. And that allows us to cancel masses still. We do have one extra term. This is the extra term due to our work done by friction, which I spelled incorrectly. And now you could plug in your numbers here, or you could solve for VC first if you wanted to do a general solution. But you'll notice now our general solution doesn't match our general solution over here anymore because you have an extra term. So that's what I was saying before. This is a good general solution as long as you don't have any extra things. As long as you have potential and kinetic energy only, no work non-conservative, this is a great equation to consider using, but I would not memorize this. I just work it out. And if you do have anything other than kinetic and potential energy in here, this equation will no longer apply, and you have something a little bit more complex. All right, that's how you'd use your energy equations. Now let's look at the table. The nice thing I like about the table is it's more numbers based, and you can watch the energies as they come out here. And the first thing I'm going to do is in step 1, I'm just going to fill in all my equations along the top here. And we have done this before. You'll notice I did add a couple columns in here for potential energy from springs. And so we have 1/2 kx squared. And we can solve for our spring displacement delta x square root of 2 pi over k, which looks very similar to our velocity equation. I also added in a column for our work non-conservative. And I'll show you how to handle work non-conservative using an energy table. It takes a little bit of trickery, but it does work. And our total energy is the sum of all of our forms of potential energies, and I'll show you later how to take into account any gains or losses we have from work non-conservative. Remember, work non-conservative can be both positive or negative. Friction is a case of non-conservative energy that's negative. It will also always take away energy from you, thermal energy in the system. But I can have an external force, like a rocket or a dog pulling us, that adds energy to the system as well. So I could have a positive or negative line item for work non-conservative. Next step, we'll fill in our knowns. And at each point along the curve, we know what our different values are for example, we started at 2.5 meters for A as the height. Down at B, we drop down to 0. At C, we're still at 0. When we go back up to D, we're not going to go back up as high because we're going to lose some energy in this line due to work non-conservative. So our D is an unknown height. Then we'll turn around, we'll drop back down to 0 again at C. Once again, on this line, we're going to use that line that I have from C to B. That's going to be our work non-conservative, so we're going to lose some more energy there. We'll get back over to B. We're still at 0 height. And then we're going to go up to some new point at point A. And you notice I'm using primes here, and I probably should use a prime over here at C prime, B prime, A prime to show you that's the second time we've passed through those points. And then we get up to our maximum height, which will be even lower than this point over here. And we'll drop down to B again down at 0, and I could call this a B double prime, so it's the third time I'm passing through it. And then we're going to lose more energy, and so on and so forth. So we're going to go back and forth, and every time we pass over that friction surface, we're going to do some work non-conservative, and we'll calculate those in these lines. You'll notice we have no springs, so I just scratched those columns out. For velocities, everywhere over zero velocity, at any high point at point A and D, I'm going to put in a 0. Although all of our other heights, our velocities are going to be unknowns that we're going to figure out. Our work non-conservative on our frictionless portions of the track is 0, so I put zeros in those frictionless portions of the track. But whenever we go between B and C, or C to B, that's where I'm going to be working out my work non-conservative. All right, so that was the first point, is just to fill in our known values for heights, velocities, and in this case work non-conservative as well, and we knocked out our springs. So remember what we're doing for our color coding here. Anything that's in green was something we did in the last step, and I'm showing you our current things we're working on in red. So let's take our known values and calculate the energies associated with them. And I showed my work a little bit here. I've got 2.5 mgh, 2.5 times 10 times 7.5, and I'm using 10 meters per second squared, not 9.8. And so my initial potential energy is 1,875 joules. Our initial kinetic energy is 0 joules. And similarly, we've got a lot of zeros showing up elsewhere that I filled in. But the key is, this gives us in our first line, we happen to know our total energy, and that's our next step. And you'll notice we're still holding off on working out the work non-conservative numbers, and we'll do that eventually. You'll see what happens next and soon. So, as I said, our total energy we happen to know for line A. And of course, if I know the energy for time A, that also lets us know where it will be. The total energy point B will be the same, because conservation of energy tells us the energy doesn't change. Well, it doesn't change for A, it doesn't change for B, but then we have a thermal loss from B to C. So we'll have to come back later and we'll fill that out. You can do that right now if you want to, but we're going to handle it a little bit later. I'm going to stop right there at filling out our energies, though. And let's go back, let's work into these blanks for our kinetic energy. So we can actually work out our kinetic energy, because we know if we have 0 joules here and 1875 here, this has to be 1875 here as a total. And then once again, our next step will be work backward again. I'll find our velocity at point B, and we can just toss in our equation up above, and we get 7.07 meters per second. A little bit faster than we were working with before. With our pendulum bob, because we're up at 2.5 meters, not 1 meter. Now, that being said, we've got our first 2 lines filled out, but now we stumble into this problem where we've got, going from B over to C, we have some energy that's lost due to work non-conservative. And when we come back the other way, from C to B, we lose some energy again. And we go from B back to C again, we lose that energy again. So the question is, how do we figure that out? Well, how do you figure out work non-conservative from B to C? Well, draw a free body diagram. Whenever you have work non-conservative, draw a free body diagram. It's based on non-conservative forces. So we've already seen this free body diagram before, so I won't explain it again. We saw this when we did the energy equation method. And we figured out, here are the numbers that were associated with that. Turns out that as you go from B over to C, you lose 350 joules of energy. Your force due to friction times your displacement times the cosine of 180 degrees between those two gives you a work non-conservative. And I'm sorry, this should be a negative here, a negative 350. And there's our negative 350 that bounced into place here. And it turns out we've got negative 350 joules lost to thermal energy. So that energy is still in our system, so don't think it's lost. It's just in a form that's not recoverable and won't go back into potential energy or kinetic energy easily at all. So what I'm going to do is I will take that negative 350 joules and I'll subtract it from my 1875, and now my new total mechanical energy, and remember, mechanical energy is comprised of my kinetic and potential energies, my conservative forms of energy. So what I'm going to do is I subtract out the non-conservative energy, and here's what's left for conservative energy. I've got 1525 joules. And of course, as I go from A to B to C, I've lost the 350 joules, but from C to D, I'm on a frictionless surface again, and so my total energy won't change. It'll stay back at 1525 joules. And as we drop back down to C again, it'll still be, my total energy will still be 1525. Now I'm back at point C, and I'm headed across the track again, the friction portion of the track, over to point B. The question is, if I go the other direction, from right to left, from C to B, what will my work be? Well, what changes on my free body diagram? My displacement is now moving to the left. I'm sliding to the left, which means my friction is to the right. My normal force and gravitational force don't change. My mu k doesn't change. So everything is the same with the exception of my displacement vector and my friction vector have just flip-flopped. But we still have a 180 degree angle between them, and I still have a negative 350 joule loss. And so every time I pass across this entire track, I'm going to lose 350 joules of energy. And once again, I would just step through the process of subtracting that away from my total energy. And I can work out, if you think about this, I can just work out this whole right-hand column now that I know what my energy is dropping across this track every time I run through the whole thing. And I can fill out the rest of my total energy column using that methodology. All right, so I should actually have a negative 350 joules written right in there as well. So from that point, you can use that same methodology with the table to back into the rest of your values, and you can finish the rest of that example problem on your own. I have a handout for you that I ask you to use the same type of techniques to do the Knieval problem. It's a worksheet. And I ask you first, if you read through the instructions, I have a few questions on one page. I have this diagram you see below on the second page, and I have a nice energy table for you to use on a third page. So please follow through the instructions.